Hey. Our topic for today is what is a basis of a vector space? A vector space over a field. So first, let's start by establishing our field. We'll say that our field is all real numbers, and our vector space, we're going to say, is the three-dimensional real numbers sitting over it. So what would something in our vector space look like? We'll say U in V, and U would equal something like 1, 3, 4. Well, how can we break that down? We can break that down into 1 in the first dimension, plus 3 in the second dimension, plus 4 in the third dimension. Alright, but we can also rewrite that as saying, well, 1 times this, 3 times this, and 4 times this. And so the key to a basis is to understand two concepts. The first one is spanning sets. Now, if I span something, it means that I can create anything, any vector in the space from anything in this set. So for example, we created the vector 1, 3, 4. We can also create the vector, 5, 2, 8, using that same sort of practice. 5 times a 1 in the first dimension, plus 2 times a 1 in the second dimension, plus 8 times a 1 in the third dimension. So really, I can take any combination of scalars A, B, and C, as long as they're real numbers, and then multiply them by these vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And that can get me any vector A, B, C, which will always be in the three-dimensional real numbers, our vector space. So we're going to go ahead and refer to this group here. We're going to call this beta. Alright, so we've shown that beta spans R3, because I can make anything in R3 just from multiplying a number by these vectors and smacking them together. So we write that by saying the span of beta is equal to R3, in this case, V. The other thing that we have to do when creating a basis is look out for linear independence. So if we take what we have beta to equal 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now let's say we also include something like 1, 0, 3 in there. Why is this no longer a basis? Well, that is because we are no longer linearly independent, because this can be made through a linear combination of these things. If I go ahead and take my first basis term and my third basis term and say 1 times this plus 3 times this, 1, 0, 3. Therefore, this doesn't even need to be in our basis. And if we get rid of it, we have returned to linear independence. Linearly independent. Great handwriting. Which we can also write as just L.I. for shorthand. Alright, so we've shown that beta spans V we've shown that beta is linearly independent. Therefore, beta is a basis for V. Pretty simple. Now, this gets into more complex terms and more kind of confusing visuals when eventually you're looking at bases for like a polynomial. But it's the same sort of thing where I'm just saying like, oh, how can I make the polynomial 2x squared plus 4x plus 0 plus 1 plus 3 da 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 da. Yeah, that sort of thing. And you can do the same thing with matrices of any dimension. But yeah, that's all. Thanks for watching, and bye-bye!